Okay, so this is sort of my voiceover for my problems for our calculus final project. I did the first half of the presentation and then Emma did the other half, and then we double checked each other's work, but we're only going to explain the half that we did independently since we're separate right now and we can't be in each other's videos. If you'll see, like on my slide, it'll tell you what type of problem I'm doing. It's almost in order, and then it's not because I did some of the end stuff too. And then it'll have the steps I followed. If you look at my paper, these are sort of the steps that I followed when I was solving the problem. I'm hoping that'll help you understand when you're grading, and I'll go over that in a second. And then it has my actual work. This is the paper you're looking at now, which is what I'm going to go over in this video, to sort of explain my work, so you don't just have to look at like the paper on the screen. So I sort of have like a voiceover explanation. Hopefully that'll make grading it a little bit easier. But anyways, I'm going over factoring a limit first. I did a polynomial limit. I'm hoping that this is correct. I have an x squared term, an x, and then this number. My question was the limit as x approaches -5, and then this was my function. When I plugged in -5 and just tried to solve for it right out, I got 0 over 0, which was like what the problem was supposed to be. So what I have to do is factor using like the square and find, I had to find what added together, like these two numbers to get the positive x that's up here, and that multiplied to get -20. And I did this by just looking at common factors and just kind of putting it together like we always do. And so I got x plus 5 and x minus 4. And what I knew was something had to divide out from the numerator and the denominator for it to be different. I couldn't just like have the same equation. Something had to divide out. Like I couldn't just keep it as is. Otherwise, it was just going to solve out the same. So I decided that I was going to divide out x plus 5 just because it worked for both the numerator and the denominator. So I was able to divide it out and have a different problem. So that way when I plugged in -5, I was able to actually get like a real numerical answer, which was -9 over 2. So that's kind of what I did here. I just used the square method, the completing a square method, so I could divide out a common factor. Then on a limit with a radical denominator, again, this was one of the ones where I tried to solve for it by just plugging in the limit value, and I got 0 over 0. So I multiplied by the conjugate, which is right here. So since my original equation was this, I multiplied by the numerator and the denominator by the root of x plus 5, which is the opposite of this, like the opposite sign here. And you can see that here, right here, multiplying by this is just like multiplying like 1 over 1. Like it should divide out and not really mean anything, but it's a way to sort of like mess with the function, so you can just sort of move things around to get a different answer. And when I did that, I was able to like cancel out some stuff on the bottom and the top, and I was able to get just a root x plus 5 on the top and a 1 on the bottom. And then when I plugged my original limit value, which was 25 in, I was able to get my limit is 10. So that's sort of what happened here. This is just like me distributing and all that. So that's my math there. If you see, it's like simplified. I have all my steps written out. Then my next one is the limit definition of a derivative. So my limit definition is f of x plus delta x minus f of x over delta x. And this is derived from sort of like the slope equation, where change in x is, well, like delta x is change in x and stuff like that, and x is like your original x coordinate. And it just finds like the change in the slope, which is what the derivative is solving for. So we've gone over that a lot in the past. And you do it when limit of delta x approaches 0 to get your derivative. And then this was my function for this example. So the first thing I did was substitute f of x in for the limit definition. So when I did this, if you see, I have a big bracket around, and then I have where I have a 6, x squared. I put the x plus delta x in for the x, and then I squared everything inside, and then the 6 is multiplied on the outside. Then it's plus, we have a 4x, so it's 4x plus delta x, and then plus 2, and that's in brackets, because those are like their own terms. And then minus and then in parentheses, because you have this like negative here, and that negative is going to distribute out all of this, and then it's just f of x here, so you just put the equation in here. So it's the same thing that was there, but it's in parentheses because it's going to be negative, and then all of that's over delta x. You don't have to put anything there, it's just delta x. And then I simplified that out. This is just sort of my math. It's a lot of distributing. You can look at my work there, double check that. I checked it with the power rule. I know that wasn't like my job to do, but I did, so I like my answer should be right, because it's just a simple one. But basically, once I divide everything out and like divide out a delta x from everything, I should get a 6 delta x plus 12x plus 4. And then when I do that, I'm finding the limit as delta x approaches 0. So the 6 times delta x will become 0, and then it'll just be 12x plus 4, which makes sense with the power rule, because this 4, it'll be like 4x to the 1, and then the x is going to go away, but the 4 is going to be times 1. And then this is going to be like 12x, and then it's going to take 1 away from the power. It makes sense with the power rule. So that was my point there. Yep, that was those problems. Now we have the position and velocity and acceleration ones. I didn't know if you didn't specify if you wanted a graph here. I originally had one, but then I took it out because it didn't say you wanted one. And I just did that the first derivative of a position first time function is going to be the velocity, and then the second derivative is going to be the acceleration. And then I just did the power rule to find that, which was super simple, so I'm not really going to go over that one too much. That's sort of the process that I followed. And then for my graphing derivatives, this was my original graph. I know it ends up getting a little messed up. I'm sorry, I can't draw graphs. But basically, it was like a basic, I think it was an just regular x squared graph. I had it on Desmos originally, but I didn't write down the function because we didn't need to have the function. And also then, like, I don't know, I just didn't have the function. And then first thing I did was determine the inflection points, which is where the slope is literally 0. Like if you did the derivative, it's going to be nothing. And this is usually where like it plateaus, usually like on the vertex of a parabola. Like if you have like a sine curve, it's like every time it like stops at the top and like at the bottom, because it's sort of like almost straight there. Like if you look at that point, it's like vertical line. Like I don't know how to describe it, but we went over it a lot, so I kind of remember that. And then I determined where it was moving positive and negative. Like here it's moving upwards and then like in the positive direction, and here it's accelerating in the negative direction. And what I mean by that is like the slope is slower here than it is here. I didn't draw it that good, like, but I do it better here. Like if you look, like it's sort of more rounded and then it goes up straight. So that means it's getting faster in the negative direction here, making it more negative. And then it's getting faster in the positive direction here, which is why it's kind of like this like down curve, then goes to the x-axis, then goes up. I didn't put it here, but any point where you have the inflection point, it's going to go through the x-axis. That's something we went over, so that's sort of why we have this little intersection here. But yep, that's what I did. Ta-da, the end.